Hello class, Professor Anderson here. Let's talk a little bit more about impulse. And let's talk about the impulse of a superball bouncing off the wall. And let's make sure we get a decent picture to start with. Here's our wall. Bricks in the wall. All you are. And there we go. Our ball comes in, bounces off the wall. So if this is, say, the positive x direction, then we can label these as Vx initial, Vx final. And we'we'll have to be a little bit careful about the directions associated with that. Now, if it's a very good superball, that means that it will bounce off with nearly the same speed as it went in. Okay? Nothing is a perfect superball, but in the limit that it is a perfect superball, it will bounce off with exactly the same speed. Okay? So we can take that into consideration. Let's ask the following question. Let's find a few things. Let's find the impulse. Let's find the average force, and let's find the average acceleration of that superball. Okay. Let's try it in general, and then we'll plug in some numbers when we're done. J is the impulse. J is, of course, a vector. And J is going to be delta P, which is mvf minus vi. All right. You look at this thing and you say, the speeds are the same. So it seems like the impulse might be 0. But that is, of course, not true. You know that can't be true, because if the impulse was 0, this thing would never bounce off the wall, just fly right through the wall. Right? Something is going on there to give it a kick, to give it an impulse. And what's happening is the following. If I think about Vx final, I have to worry about the vector Vx final and the vector Vx initial. Let's start with Vx initial. So Vx initial is going to be some speed, V initial, Vx initial, but it's also a direction. It's in the positive x direction, and so we say positive I hat. Vx final, which is a vector, it's a velocity, is Vx final, the speed, but it's in the negative x direction. So it is minus I hat. That minus sign I can move out in front, and so we get a minus Vxf I hat. And this is the key, because now when we go back to this equation, what happens? J is equal to m times Vf minus Vi. And now we know what they are. It is Vx initial times I hat minus, sorry, I had that one backwards. Vx final is this, minus Vxf I hat, and then we're subtracting Vx initial times I hat. And when I have minus and minus, I obviously get 2 of them if they are the same. And so in this case, we're going to end up with negative 2m Vx initial. Okay, so it's that directionality that is important when we're looking at the deltas, because we're taking deltas of velocity, not deltas of speed. All right, so that's our J. Let's see if we can calculate F. So for our superball with a perfect bounce, what we found was the J, the impulse to that superball, was negative 2m Vxi, and it's got a direction associated with I hat. It's going to go back in the direction that it came from. What about the average force? Well, remember that J is the integral of F dt. So if I have some complicated force as a function of time, whatever it looks like, I can always calculate the average of that thing and label that F bar. And in that case, this becomes F bar delta t. Okay, the area here under this F bar is going to be the same as the area under the Gaussian curve if you multiply by this delta t. Okay, and so now you can calculate exactly what F bar is. F bar is just impulse divided by delta t. And in this case, we know exactly what the impulse is. It's minus 2m Vx initial. I'm going to divide that by delta t. And it's in the I hat direction. And so it's a negative force. Right? We drew a positive force just for simplicity, but it's really a negative force. It's going back in the direction that it came from. It's trying to push that superball back to where it came from. All right. What about the acceleration? Well, once we know F bar, we can calculate the acceleration just from Newton's second law. A bar is F bar over m. And now at this point we can try some real numbers and let's see what happens. Okay? So let's go with the following. Let's say that VI is 20 meters per second. All right, that's pretty fast moving superball. Right? 20 meters per second is about 40 miles per hour, but you could throw something at 40 miles per hour. That's not too hard to do. What's m? M is, let's say, 10 grams. And let's say that it's in contact with the wall for, let's try 1 millisecond. We had some other numbers earlier, but let's try 1 millisecond. That's a decent number to start with for how long a superball is in contact with the wall. And now let's calculate J. All right, J is right here, negative 2m. So it's negative 2 times 10 grams, which is 0.01 kilograms, times VI, which is 20 meters per second. And when I do that, what do I get? It's negative 40 times 0.01, which is negative 0.04. And the units are kilogram meter per second. All right, some number. We don't know if that's a big number or a small number, but it's some number, right? What about the force? F bar, we said, was J over delta T. J is right here. It's negative 0.04, and we are in SI units, so we just leave it like that. And we're going to divide by 1 times 10 to the minus 3. 1 times 10 to the minus 3 on the bottom. Up on the top, we have negative 4 times 10 to the minus 2. Did we do that right? This should be 0.4, right? You guys got to double check my math. That should be 0.4, and this should be 10 to the minus 1. Right, because we've got 2 times 20, that's 40 times, so that's 4 times 10 to the 2. And then we're going to do a 10 to the minus 2. All right, let's back it up. We've got to do this math right. This is the beauty about video, right? You edit all this stuff out. You can just go like this, and then the answer will appear. Okay, so this is negative 40, which is 4 times 10 to the 1. And then we're multiplying by 0.01, which is 10 to the minus 2. Okay, so J is going to be negative 4 times 10 to the minus 1. We'll leave it in scientific notation. And the units are kilogram meter per second. All right, what is F bar? F bar is J over delta T. Let's go up here and do this. F bar is J over delta T. And J we just said was that, negative 4 times 10 to the minus 1. And delta T we said was 1 millisecond, so that's 1 times 10 to the minus 3 seconds. And what do we get if we do that? We get a negative 4, and then we have to add a 10 to the 3 up there, but we're subtracting 1, and so we get negative 4 times 10 to the 2. Units of force are, of course, newtons. All right, that sounds like potentially a big number, but we're not exactly sure. Let's compare acceleration to something that we know, which is gravity, which is 9.8. Let's see how big this acceleration will be. Acceleration is F bar over m. F bar, we just said, is minus 4 times 10 to the 2 newtons. M, we said, is 10 grams, which is 0.01 kilograms. So this is minus 4 times 10 to the 2 over 1 times 10 to the minus 2. And so we get negative 4 times 10 to the 4 meters per second squared. And that's a pretty big number, right? Remember, G itself is 9.8, which is on the order of 1 times 10 to the 1 meters per second squared. And now we're dealing with something that is 4 times 10 to the 4. So this is 4 times 10 to the 3, 4,000 times bigger than gravity. And these are fairly realistic numbers here. If you take a superball and throw it pretty hard against the wall, these numbers are pretty close to realistic. And that thing is now accelerating at 4,000 times gravity if you just dropped it, which is kind of weird to think about. Okay? But this is really what happens. This is why superballs don't last so long. Right? Golf balls, same thing. They don't last very long. Even billiard balls don't last that long because they're hit with these big, big accelerations, these relatively big forces. Okay, questions about that stuff? Okay.